Physicists are worried because they have a big problem. They've been saying that information can't be destroyed. This is basically a law of nature. But then they also say that when stuff falls into a black hole, it's gone forever. And those two things can't both be true, so something's got to give. Now, I wouldn't normally get excited about physicists' inability to agree with each other, but this time they might actually be onto something big, possibly even revolutionary. Like, what if there's another universe? Let's start out with why physicists are in this weird situation. The idea that information can't be destroyed is often called the no-cloning theorem. And it means that you can't take some information, put it into a black box, and then take out of that box an exact copy of what went in. If you do that, you would be creating new information, and that's impossible. You can never get more information than you started with. There are all sorts of ways that this comes up in physics. For example, consider two particles that are linked together in some way. Maybe they were created in the same event, or maybe they're both parts of a larger system like a molecule. These are called entangled particles, and we know from experience that if you know everything there is to know about one of them, you know everything there is to know about the other. Like if you knew the spin of one particle, you would automatically know the spin of its partner. It has to be that way. Otherwise, you could use those particles to create an exact copy of an unknown input, which would be information gain. Now, if the no-cloning theorem is right, then anything that falls into a black hole must be made of information that came from somewhere else. Because if it was made of information that was already inside the black hole, then that would be information gain. So any information that goes into a black hole must come from outside. And because of the no-cloning theorem, once that information goes in, it can't come back out. And so anything that falls into a black hole is lost to the outside universe forever. And this is where physicists run into trouble, because according to another well-established principle of physics, information can't be destroyed. This is the second law of thermodynamics. In a closed system, entropy wins every time. It says that any configuration of mirrors and lenses that you set up in a room will inevitably end up with dust bunnies in all the corners, not just for that room, but for the entire universe. This is obviously a very poetic idea, but it's also mathematically well defined. Physicists quantify entropy as a property of any system called the von Neumann entropy. And here's how it works. Imagine you have a coin. If it lands heads, that's one state of affairs, and if it lands tails, that's another. So the possible states of the coin are 0 and 1. That's binary, but really any two numbers would work. Now imagine you flip the coin twice. There are, for possible outcomes, heads, heads, tails, 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 heads, and heads, tails. So now the possible states of your coin flip are the numbers 0, 1, 2, and 3. Each outcome is a different linear combination of these basis states. If you want to figure out how much entropy there is in your system, you need to find what's called the density matrix. And this is just a fancy name for a table that tells you the probabilities of finding your system in each of those states. So for our coin flip example, you'd have a row for each possible state and a column for each outcome. And you'd put down the probability of that outcome occurring in the corresponding spots. In this case, if you flip a fair coin twice, each outcome has a probability of 1/4. Once you have that table, you take each probability, multiply it by the logarithm of that probability, and then add them all up. And that is your entropy. The more possible states there are for your system, the more entropy there is. Now that's for a simple example with only 4 possibilities. But the math generalizes to systems with a basically infinite number of possible states. For example, for a single particle, there's an infinite number of possible positions and an infinite number of possible speeds. And so there's an infinite number of possible states. For a collection of particles, you multiply the number of possibilities for each particle together, and that gives you the total number of possible states for the whole system. And when you plug that into the entropy equation, the answer is unsurprisingly infinity. So that's why physicists worrying that something has got to give between the no-cloning theorem and the second law of thermodynamics. Things that fall into black holes can't carry information with them because that would violate the no-cloning theorem. But at the same time, that information can't be destroyed, which means it has to go somewhere. And the most obvious place for it to go is into another universe. That's right, we're talking about the multiverse again. I do and love talking about the multiverse because people usually bring it up to talk about some crackpot theory in which the universe splits every time someone makes a decision and every possibility plays out in its own universe. This idea is known as many worlds interpretation. And it's fine if you want to play make-believe, but there is absolutely zero evidence for it. And it's ruled out by experiment, so it's not real science. The only reason scientists even bring up the multiverse is to solve problems like the black hole information paradox. Stephen Hawking first pointed out that black holes seem to violate the second law of thermodynamics in the late 70s. He said that since black holes evaporate, all that information has to go somewhere. At the time, Hawking thought that maybe something did get destroyed. Then later he changed his mind and said it goes into another universe. But Hawking wasn't talking about the many worlds interpretation. What he had in mind is more similar to an idea called the eternal inflation multiverse. According to this idea, the universe is full of wormholes. Wormholes connect distant points in spacetime, and some of them connect to universes that are slightly different from ours. Spacetime is always bubbling and fluctuating, and sometimes those fluctuations open up wormholes. When a wormhole opens up, matter and energy pour through and new universes are born. You can think of it kind of like a pond with ducks swimming around in it. The pond is our observable universe. Ducks represent clumps of matter, and the surface of the pond represents space-time. As the ducks move around, they make ripples in the pond. These ripples represent fluctuations in space-time. Those ripples can get big enough to create new ponds. And when they do, more ducks or universes pop into existence. Hawking suggested that the information from collapsing black holes makes its way through a series of wormholes and eventually ends up in another bubble, another universe. What's interesting is that the math actually does seem to work if you assume that stuff goes into another universe. That doesn't mean that Hawking was right, it just means that the math works out. In fact, there is another interpretation of quantum mechanics that also seems to resolve the paradox without the need for another universe. This interpretation is called consistent histories. Basically, it changes our notion of what it means for something to be a physical system. In the consistent histories interpretation, physical systems only exist as a collection of possible histories. So a history is the thing that exists, not a specific moment in time. The idea is that you describe the history of a system by writing down all the possible histories. And then you say that the actual history of the system is the subset of those possible histories that are consistent with each other. Now that sounds kind of vague and abstract, but the point is that once you've identified the actual history of a system, you can calculate the entropy. And in the case of a black hole, it turns out that the entropy of the system matches what physics predicts, which is nice, but that's not the interesting part. The interesting part is that in this framework, you can calculate the entropy of what goes into the black hole, but you also have to calculate the entropy of what comes out. And if you do that correctly, you find that the entropy of the stuff that comes out is exactly the same as the stuff that goes in. So it looks like the second law of thermodynamics holds up either way. Either stuff goes into another universe or it doesn't. But the cool thing is that in the consistent histories interpretation, you don't need another universe to do that. Personally, I am going to reserve judgment on whether either of these ideas is correct until we can rule out the possibility that black holes do destroy information. Right now, we don't have the technology to test this, but maybe one day soon we will. And if that happens, I promise I'll come back and tell you all about it. Thanks for watching this episode. We've made thousands of educational videos over the years, and we've been able to offer them for free because of our patrons. So, to all of our patrons, thank you for what you do to make this happen. If you're not a patron but you want to learn more about what that means, you can go to our support page.